Well, good afternoon. It's 12:16 on Wednesday, the 14th of November, 2018. Supposed to be Calculus 3 class, and right now I'm the only one in the room, so hopefully some more will be coming in a bit. Okay? Couple of things to announce, and I think probably all of you know this already, but in case any of you listen to it before the time is over, just a couple of things. One is that I had a fairly productive Friday last Friday, and that no one else was in the office, so we had several people come by periodically, but I got a lot of grading done Friday and some other things I had to take care of. But anyway, then over the weekend I had little bits and times here and there that I got a little bit more grading done. But then Veterans Day Monday, or the holiday for Veterans Day, on Monday, it was so rainy and miserable outside. After I ran some errands in the morning, I had a lot of the afternoon to try to catch up on grading, and I made great progress up until the point of where my red ink ran out, and I could not find another red ink pen at the house. Probably didn't look everywhere I could have, but all the places I looked, I couldn't find another one. So at that point, I started putting grades in Blackboard, so I got in addition to getting the grading done for this class, I got your grades in Blackboard as well. Now, I missed two of my classes. The pages were just a weird way of how I did things, and I skipped right over two of my classes. So you're the only ones. I mean, the other classes, which I don't know, 4, 6, 5 other classes, got their grades in, but those two did not. So I just want to let you know that. The grades are out there. They're up to date unless something's been turned in this week. Next. I guess all of you know that next week is Thanksgiving week. And as such, of course, Thursday and Friday are state holidays, so the school is completely closed those 2 days. However, there are no classes Monday, Tuesday, or Wednesday. The state Alabama 2-year college system, community college system, has its annual meetings they begin Sunday evening and then go Monday and Tuesday. And this year they're down in Mobile, which I'm not about to go down there just for the meetings. But anyway, they are meeting then. We will have those who don't go there, which is most of us, we'll have professional meetings on the Birmingham West campus Monday and Tuesday, and then Wednesday, I think it's usually an office day that we just have time to catch up things and to take care of things in the office. So if you have any business to do at the college, there'll be no classes at all next week. But if you have any business to settle with the college to do or anything like that, then please, the college is open. All the offices will be manned, though they may not be fully manned, but they'll have somebody in all the offices Monday and Tuesday, and certainly Wednesday morning. Okay, so if you have business to take care of with at the college, please come in and get it taken care of Monday or Tuesday. Wednesday, they sometimes let people go early on Wednesdays, okay, and some departments might let them go earlier than others. Seldom will it be before noon, so there should be people in all the offices Wednesday morning. But I wouldn't bank on catching all the offices open on Wednesday afternoon. Not all afternoon anyway. So please, if you have business to do with the college, try to take care of it Monday, Tuesday, or Wednesday morning. All day Monday, all day Tuesday, but Wednesday morning. You might still catch someone Wednesday afternoon, but the odds are not very great. And again, if you're looking for faculty, we will not be in our offices most of the time on Monday and Tuesday. We're going to be in professional meetings Monday and Tuesday, but then Wednesday we will be in the offices up until if they decide to let us go early, up until that point. So, for instance, 1 year it seemed like it was 1 o'clock. It seems like another year it was around 2. It may have been 1 year they let people go at noon. I can't remember back. But anyway, they typically, but not always, let people go a little early on Wednesday. But It's not guaranteed. Okay, those are the major announcements I know about. Thought maybe somebody else would come in, but they haven't. So let's continue. Now, where I have marked in my text, we're in Chapter 13, Functions of Several Variables, in 13.7, Tangent Planes and Normal Lines, and Example 5 is where we left off last time. Now, on the slide I have Example 2. The reason for that is they didn't do 3, 4, or 5. I think they'll pick up with angle of inclination of a plane, but not Example 5. So let's do that one on the bottom part of this page. Okay, let me get my pen set up. Okay. Sorry. I crammed down as much lunch as I could in the 15 or 20 minutes I had between classes, so the throat's not really there all the way right now. All right. It says finding an equation of a tangent line to a curve. Okay. The example 5 says find a set of parametric equations for the tangent line to the curve of intersection of the ellipsoid, and here's the ellipsoid x squared plus 2y squared plus 2z squared is equal to 20. Okay? And the paraboloid x squared plus y squared plus z is equal to 4. Okay? Now at the point, and it says find the set of parametric equations for the tangent line to the curve at the curve of intersection of the ellipsoid at the point 0, 1, 3. Okay, at that point 0, 1, 3. Now they have the picture in the book. I really don't want to draw that. I hope you can figure that out on your own. The way to think about the ellipsoid, the top thing there, is divide everything by 20. And you'd have x squared over over 20 plus y squared over 10 plus z squared over 10 is equal to 1. Okay? Now that tells you that the long axis of this ellipsoid is the x-axis, and you see the figure in the book is that. The y and z are equal length, so you've got circular cross-sections in the yz plane, but an elliptical cross-section in the xz plane. The xy plane would also be elliptical. Okay? So then the paraboloid cuts through that ellipsoid and breaks through at the top, you might say, z-axis, because this is the paraboloid. Since z is not squared, that's the axis of rotation of the parabola around the z-axis. Okay? Now, cynic that I am, it says at this point 0, 1, 3, I want to make sure that that point is indeed both on the paraboloid and on the ellipsoid. So let's try the ellipsoid first. That would be 0 for x squared. That would be 2 for the next term, because 1 squared is 1. It would be 2 plus 3 times 9. 2 times 9 is 18, plus 2, sure enough, is 20. So it is on the ellipsoid. How about on the paraboloid? 0 for x again, 1 for y, 3 for z, 1 plus 3 is 4. Sure enough, it is on the ellipsoid, the paraboloid as well. So we do know that this point is on both of them. Okay. Now, what we need to find, we're looking for the parametric equations for the tangent line to the curve of the intersection of these two shapes at that point. Okay? Now, Whereas back when we were doing differential calculus, and most of the times when you began a problem, you would say, where do you begin? And the pretty safe answer was, take a derivative, okay? Here, where you're finding the same type things, but in 3 dimensions, you'll typically, in many instances, find the gradient. So that's what we're going to do first, find the gradient of both the ellipsoid and the paraboloid, and we'll plug in the values at 0, 1, 3. Now the gradient is going to give you the direction of curvature, basically is going to point toward the center of curvature. Let's see, is that right? Yeah. Place of maximum increase of the tangent line. So it will be a tangent line. So let's go on and did it. Let me go back and get my verbiage right. We're going to be using theorem 1313, equation of a tangent. Well, we're not doing a tangent plane. We're doing tangent lines. Sorry, not that one. But if you go back to when we started off with gradients, properties of a gradient, the del F, 3-dimension, the theorem 1311 is mostly 2-dimensional, but you can extend it to 3. Make sure they don't have that in here somewhere, so we can just deal with 3. Okay. Yeah, directional derivatives and gradient for the gradient of F is defined as in 3 dimensions. This is on page 927. That just tells you how to get it. The direction of maximum increase of F of your function is given by the gradient. Okay, the direction of maximum increase. Now, that's typically not a tangent line, okay? So, but just hang on to the thought. It's the direction of maximum increase, okay? So let's do the grad. I'm sorry, I drew it upside down. Do the gradient, sometimes called grad. The symbol is called del, and I'm going to do it for the ellipsoid. So I'm going to call it E. In the book they called it F for some reason. I don't know why, but just because F and G they like to use as functions. But let's do it for the ellipsoid. What is that? It's the partial derivative of this equation right here with respect to x, which would be 2x in the I direction plus 4y in the j direction plus 4z in the k direction. Okay, that's grad of the ellipsoid. The gradient, and by the way, that's a vector, so I like to put the vector there. In the book, their little dells look like they're bolded, which indicate they're vectors. Okay, let's do the same for the paraboloid. I'll call this the grad of P. Here would be 2x in the I direction plus 2y in the j direction plus 1 plus k. Okay, 1 in the k direction. Okay? Now, let's calculate those at the point in question, which is 1, 0, 1, 3. So grad for the ellipsoid, the gradient of the ellipsoid at the point 0, 1, 3 would be x would be 0, y would be 4, 4j, and z would be 12k. That's the direction of maximum increase of the curvature of that circle, of that surface at that point, okay? Whereas your grad for the paraboloid at 0, 1, 3 would be 0i 2j, because 2 times 1 is 2, plus k. That never changes because it's just k, okay? So there is your gradient for the paraboloid at that point. Now, these are pointing in directions of maximum increase for these surfaces, okay? Now, the cross product of those two gradients is a vector that is tangent to both surfaces at the point 0, 1, 3. Now, if you go back to all right, let's go back to the definition of the tangent plane, even though we're not dealing with planes, we're just tangent lines, but tangent plane is a plane full of tangent lines, okay? So we sort of are. If f is differentiable at the point, which it is, we just did for both of these, on the surface S given by that, and we could have just moved the minus 20 and minus 4 to the other side of that, then the plane through P, through that point, that is normal to the gradient, that's the vector in, and here we're talking about a plane now, normal to, or perpendicular to the gradient, okay? And the gradient is the direction of maximum increase. And is called the tangent plane. The plane that is normal to the gradient. Now the gradient and I wish I had said the other one first, and so let's do it. The line through P having a direction of the gradient is called the normal line. So that tells us that the gradient is going to be a line perpendicular to the surface there, the direction of maximum increase, okay, from any direction, okay. Now, it's perpendicular, okay. The plane that is normal to that, or at 90 degrees of that, is your tangent line then, tangent plane, okay. Now, so the gradient gives you something normal to the curve, both of these curves, at that thing. Two different vectors here, okay? They're both normal to, one of them's normal to the ellipsoid, one of them's normal to the paraboloid, okay? We want something that's perpendicular to both of those, okay? Those normal lines, perpendicular to both of those. What's that? But a cross product, okay? The cross product will be perpendicular to both of those, and if they're perpendicular to the normals, that means they have to be tangential. So that's why we're doing the cross product between these two. And it really doesn't matter which order. I'm going to do ellipse cross the gradient of the ellipse cross the gradient of the paraboloid, ellipsoid and the paraboloid. It really doesn't matter. So let's do the gradient, the cross product. If you remember, I can't draw it all. Del E cross del P would be, how you do those, I, J, K, put that across the top, then put the coordinates the vector coordinates here, 0, 4, 12, 0, 2, 1. Okay? And let's do the cross product. Now, the easy way to do that is just repeat your first two columns, I, J, 0, 4, and 0, 2. Okay? And what we're going to do, okay, I hope you've already seen this, but if you haven't, let's do it. Okay? Let's do our downward slope, and that's going to be 4I, downward slope here, 0, 0. Okay? And then the upward slopes would be 0, minus 24I, and 0. Okay? Well, guess what? This will be minus 20I. Okay? And that's exactly what your the cross product is. That is a tangent line, okay, that's tangent to both of those curves. In other words, the intersection of those curves. So the tangent line to the curve of intersection of these two surfaces at the point 0, 1, 3 is a line that is parallel to the x-axis, minus 20I is parallel to the x-axis, passes through the point 0, 1, 3, because the 0, 20I is minus 20 times I plus 0 plus 0, j, and k. The direction numbers are 1, 0, and 0. Okay, now let's go back and remind ourselves what the direction numbers are. We did that at the end of the last example, and that came from way back. I can't remember which chapter it was. When we did direction numbers. I looked it up last time. Seems like, oh goodness, way back. Maybe chapter, I think it was further back than 12, but let me just see. Direction numbers. I did this last time out of the direction. Numbers. 787. I just remember getting that number. Okay. 787. All right. Lines, yeah, chapter 11, 11.5. Lines and planes in space. Parametric equations for a line in space. A line L parallel to a vector V, ABC, passing through a point P, X1, Y1, Z1, is represented by parametric equation X is equal X1 plus AT, Y is Y1 plus BT, and Z is Z1 plus CT. The direction numbers A, B, and C are all non-zero. Then you can eliminate the parameter T in the parametric equations to obtain the symmetric equations to the line, and that's what we're looking for, I think. It says a set of parametric equations, so we're not necessarily eliminating those, but we could. It's a set of parametric equations, which we're not going to eliminate completely. We are looking for parametric equations. So that is just going to be X equal T. Okay. Our vector here is this one. Okay. So the components we're dealing with, if you factor out the minus 20, that's where you get the 1, 0, 0. Okay, so it's minus 20 times 1 vector 1, 0, 0. Okay, now a line parallel, that's your vector. The 1, 0, 0 is like your vector v on page 787. Okay, it's just a multiple of minus 20. It's just, yeah. Okay, now and that's your A, B, C. Okay, that's what they're calling the direction numbers, because those are the components of the vector in which this is going. So basically A is equal to 1. So what are your parametric equations? X is equal to, now the x1, x2, and x1, y1, and z1 are your point. For our point, it's 0, 1, 3. So x would be equal to x1, which is 0, plus 1t. Y would be equal to 1 plus 0t, and z would be equal to 3 plus 0t. So what would that be? X equal 1, x equal 1, I mean t, x equal t, y is equal to 1, and z is equal to 3. There would be our parametric equations. Okay? X equal t, whatever parameter you choose for it, minus 20 would be perfectly fine. It didn't matter what it was. Y is equal to 1, z is equal to 3, because you're somewhere in, you've got to go through that point. So that's why the y is equal to 1 and z is equal to 3, certain to be there. Okay? So there are your set of parametric equations that define that tangent line. Okay, for any value t you want to put there, 17, 1, 3, negative 20, 1, 3, 4/3, 1, 3, it doesn't matter what, that will be, any of those would be on that line. Okay. Now, that's done. Let's move on to, I think they pick up, okay, yeah, here we go. The angle of inclination of a plane. Okay, we've been talking about planes in general, specifically tangent planes. Another use of the gradient, which is grad f, whatever that big capital letter f is, that's when you set up your function equal to 0. Whatever your function that's given to you, if it's equal to something else, bring everything to the same side of the thing and have the right-hand side be 0. The function on the left-hand side would then be your capital F. The grad of that, or the gradient of that function, would then be, you know, whatever it is when you take the partials in those three directions. Another use of that gradient is to determine the angle of inclination of the tangent plane to a surface. The angle of inclination of a plane, here's all that's written here. The angle of inclination of a plane is defined as the angle theta, something between 0 and pi halves. So some acute angle theta, with the exception, if the angle is 0, that's not acute, and if the angle is pi halves, that's right angle, okay? But anything in between those would be an acute angle. Between the given plane and the xy plane, sort of like this figure is showing here. Excuse me. Okay. Shown here, the angle of inclination of a horizontal plane is defined as 0. Another one that's parallel to the xy plane, that angle of inclination would be 0. And if it's anything that contains the z-axis, any plane that contains the z-axis, that would be, angle of inclination would be pi halves. I mean, it contains the entire z-axis. Okay. Okay. because the vector k is normal to the xy plane, that's the one in parallel to the z-axis, normal to the xy plane, you can use the formula for the cosine of an angle between two planes to conclude that the angle of inclination of a plane with a normal vector n is, okay, cosine of theta will be the absolute value of the dot product of n and k, where n is the normal vector and k is the vector in the z direction, okay, divided by the magnitude of n times the magnitude of k, but the magnitude of k is 1. That's a unit vector, okay? So it's the dot product of n dot k, the absolute value of n dot k divided by magnitude of n, okay? Fairly simple formula there. And just as a refresher, one of the definitions of a dot product is the magnitude of the first times the magnitude of the second times the cosine of the angle in between. So that's how we define this angle, because whatever that normal vector is, dot it with k, and that would be the angle between the angle of inclination. That's what I'm trying to say. Okay. Now, so here's example 6. Let's just turn the page here to page 936. Okay. Find the angle of inclination of the tangent plane to the ellipsoid at the point 221. And again, cynic that I am, I always check this. When x is 2, x squared is 4, 4 over 12 is 1/3. When y is 1, y squared is, when y is 2, y squared is 4, 4 over 12 is another 1/3, and when z is 1, z squared is 1, and 1 over 3 is 1/3, and 1/3 plus 1/3 plus 1/3, sure enough, is 1. So that point 221 is on that ellipsoid, okay? Now, it says find the angle of inclination of the tangent plane. Well, remember, one thing we have to have is the normal vector. Well, guess what a normal vector is? Well, technically you begin this way, though it really isn't going to make a lot of difference. Redefine this function here to be your capital F of x, y, and z to be this function, x squared over 12 plus y squared over 12 plus z squared over 3 minus 1 is equal to 0. That then gives you this function f. And like I said, all you're doing is subtracting the constant from the other side. Now, if you had other things on the other side, you subtract them too, or add them, or whatever it takes, but you got to get it equal to 0 on the other side. But for these, this is a piece of cake. Then once you identify that function, then you do the del for that function, the gradient of that function, x, y, z. Remember, this will be a vector now. So 2x over 12 would be 1/6 x in the I direction, plus, I'm going to put it this way, y over 6 in the j direction, plus 2/3 z in the k direction. All right, I'm glad that you're here. Oh yeah, flip them out. Stiff when I sit too long. Well, sometimes you press this button, it does something, sometimes it doesn't. There, it's doing something now. All right, while we're waiting for the projector to come on, let me mark you present. So I have somebody here today. Okay. Let me remind you of a couple things. Next week is Thanksgiving week. You know about that? Okay. It's Thanksgiving week, and just like everywhere, across everything, usually Thursday and Friday are both holidays. Certainly are for the state, functions. Thursday and Friday are holidays. Thursday's Thanksgiving Day. What's that?
That's next week, right?
Next week. Yeah, a week from tomorrow is Thanksgiving Day. Okay, so now stores are all going to be open like crazy because that's the biggest shopping day of the year. Typically, is the Friday after Thanksgiving because most people are off. So all the stores are going to be happy as clowns, but all the people are going to be working. Okay, because that's a very busy shopping day. But the school is. Yeah, it's called Black Friday. Yeah. Okay, that's when most of the businesses, if they've been operating in the red, they hope to be operating in the black after Friday. Okay, that's one definition for it. Okay, now, so all state offices, now I can't remember if the mail runs on Friday or not, but most things are closed on Friday, Thursday and Friday. Okay, a 2-day week, a 2-day holiday. So the college is absolutely closed Thursday and Friday of next week. But because the Alabama Community College system has their annual meetings on Sunday, Monday, and Tuesday of Thanksgiving week, the colleges are closed. No, wait, let me rephrase that. The classes are canceled. There are no classes Monday, Tuesday, or Wednesday of next week, and certainly not Friday, Thursday, or Friday. So there's no classes at all next week. Okay, now, do you also go to UAB or anywhere? No, okay. I was going to say other four-year schools may, they probably are open Monday, Tuesday, and Wednesday. Okay, 2-year college system, our annual meetings are down in Mobile this year, so bunches of them are going down there for that meeting. I'm not, okay, because it's expensive. And
Get the college to pay for it.
huh?
Get the college to pay for it.
Well, but you see, it's my budget, and I want as many other people who want to go to be able to go, because I'm so close to retirement, it doesn't matter to me.
Oh, you're the head of the math department?
Yes.
Okay.
Yeah, and so you see, I don't want to spend the money on me. I'd rather the younger faculty member go if they want to go. But the other thing, it's just a long drive, and it's they're fairly boring meetings. So I'm sorry, I shouldn't be recording that, but I don't figure it's worth it to me anyway. Younger faculty members, they probably do need the exposure. I feel like I don't. So anyway, we will be having professional development here, not in this building, but on the Birmingham West Campus. So those of us who don't go to the meetings, and that's most of the college, will be over on the Birmingham West Campus in the ACAT building. We'll be having professional meetings there. That's Monday and Tuesday. Wednesday, they usually let us come back to our offices and get work done. Thank goodness. And so for most of us, faculty members, we will be over there. So even though the college is still open, now if you need any business with the college, any of the offices or other things, every office, major office, will be open. Probably be very minimally staffed, but they will be open. So if you have any business with the college, Monday, Tuesday, now hang on to this one, Wednesday morning, okay, that would be, the offices will be open. The reason I say Wednesday morning is quite often, though it's not guaranteed, but quite often they do let people go home early on Wednesday because the next day is the big holiday, okay? And a lot of people get home and have a lot of cooking to do. So rather than having them do that late at night on Wednesday, they let them go sometime in the afternoon. Okay. That's not guaranteed, though. But what I'm suggesting, if you got business to do with the college, get it done Monday, all day Tuesday, or Wednesday morning. Because even though there probably someone will still be around Wednesday afternoon, maybe not every office you might need to get to would be open Wednesday afternoon. So I would say get it done anytime Monday, anytime Tuesday, or Wednesday morning. Okay, that would be safe. Okay, and the only time to catch faculty members probably in their offices would be Wednesday. Now, a lot of faculty members may take Wednesday off just as a personal day. That's fine too. I will be here Wednesday, until they let us go, which I'm hoping will be somewhere around 1 or 2, but it's not guaranteed. But that's usually what it's been in the past, somewhere around 1 or 2 o'clock, they'll let people go. So, though it's not guaranteed. And at that point, I'll be saying goodbye also. So just to let you know, that's next week. We won't meet again until the following Monday after Thanksgiving. I think we have probably 2 more weeks after that, and then finals or something like that. So anyway, that's what we said. All right. Now, any questions on that? Okay, what we're doing is on page 936, it's chapter 13, functions of several variables, 13.7 section, which is tangent planes and normal lines. What we're doing, I just was setting it up here, is finding the angle of inclination of a tangent plane. Okay. Now, to the ellipsoid, x squared over 12 plus y squared over 12 plus z squared over 3 is equal to 1. Okay? Now that's an ellipse that has long axes in the x and y direction and real squatty axis in the z direction. So it's kind of like a flying saucer. Okay? X's and y's are big like this with z pretty small. Okay? Now, at the point 2, 2, 1, and I validated by plugging in 2, 2, and 1 up there to make sure that did come up equal 1, and it does. Now, technically, the first thing we do, rather than using this as our function, this would be our little f. If you subtract the 1 and bring it over here and make it equal to 0, that becomes our capital F. So everything we do, we're going to get the same answer as if we didn't do that. But if you had x's and y's over there, yeah, it would make a big difference. But we don't, we just have a constant. So then, once we do that, and get our capital F, then we take the, ooh, I forgot to put F in there. That's the whole purpose of doing that. Taking the gradient of F, of that function F that we just came up with. And that's what I just did. Remember, the gradient is a partial of this thing with respect to x. That's the only term with x in it, so that would be 1/6 x in the I direction. Remember, a gradient is a vector. The function is a scalar function, but its gradient is a vector pointing in some direction, maximum increase of the surface at that point. Okay? So it's 1/6 x in the I direction plus 1/6 y in the j direction plus 2/3 z in the k direction. So partial of that with respect to z would be 2/3 z, okay, in the k direction. All right. Now, what does that tell us? We're looking for the angle of inclination of the tangent plane to the ellipsoid, that ellipsoid, at that point. Well, there's the gradient vector. Well, the gradient vector is the vector of greatest change, the direction of greatest change in the curvature of that function, and we haven't put in the point yet, but we'll do that in just a minute. Okay? And since it's at the point, let's go on and do that.
Why did you change the system of notation? Like you have
1/6 x and y over 6.
yeah, what did you change?
I just, after I did this, I thought it's easier to write y over 6. Okay, I wish I had written x over 6 just to make it easier. But I just was doing as I thought, and then I thought, oh, it's easier to write it this way. No difference. Okay. Now let's plug in the value of this point. So the gradient of f at that point, 2, 2, 1, would be what?
2 over 6.
Which is 1 over 3 in the I direction plus 1 over 3 in the j direction plus 2 over 3 in the k direction. Okay, that is the vector pointing in the direction of the greatest change in the surface at that point. Okay? Now, with that being the case, greatest change x, y, and z, that has to be normal to the surface there. So that's in the direction perpendicular to the tangent plane. Got to be, right? Okay. So that's normal to the tangent plane. All right. Now, I'm going to refer you back because that value there is normal to the tangent plane, and K is normal to the XY plane. So when they say the angle of inclination, that's the angle of inclination. Okay. Let's picture, here's the XY plane. The floor is the XY plane, okay? And your ellipsoid is somewhere up here, okay? Part of it's above the XY plane, part of it's below. We're in the part above, because this is in the first item, okay? So the normal vector here, or the gradient vector, is normal to this tangent plane, right? Here's the tangent plane. So it's going somewhere like this. We'll put it like this. Okay? That's easier for me to do. Okay? The angle of inclination of that tangent plane is the angle between the XY plane and this tangent plane like this. Okay? Well, this thing is normal to the tangent plane. The z-axis, K, is normal to the XY plane. XY here, Z's there, so K is normal to that. So if you go back to just the previous page, they give the definition of the angle of inclination, okay? And they give it this way. Cosine of the angle of inclination is equal to the absolute value of the normal vector, okay? I'll just put it as that, dotted with the k vector, which you know is a unit vector, divided by the magnitude of the normal vector. Okay. Normal vector doesn't have to be a unit vector. Okay. Sometimes it's listed as one. This time it doesn't have to be. Well, guess what? This is a normal line to the thing. It's not the only one, but it is a normal line. So we can dot it with the k. What's k in component notation? 0, 0, 1. That's the k vector, right? Okay. There's the, you can use that as your normal vector. It is normal, okay? So you can do that, and you've got to dot those two together, okay? So basically, the dot product of those two would be 1/3 times 0, that would be 0, plus 1/3 times 0, that would be 0, plus 2/3. Okay? Magnitude of that will be 2/3. Okay? Divided by the magnitude of your normal vector. Well, the magnitude of the normal vector be the square root of, this is your normal vector. No, of 1/3, square root of, yeah, 1/3 squared. That'd be 1/9 plus 1/9 plus 4/9. Okay? That'd be 4, 5, 6/9, which is the square root of 2/3. So it'd be 2/3 over the square root of 2/3. Oh, wait. Yeah, square root of 2/3. Okay? Now, that is just the square root of 2/3. Right? Because square root of 2/3 will go into 2/3 square root of 2/3 times. Because square root of 2/3 times square root of 2/3 is 2/3, right? Okay. Give me a number. Any number.
I think it's
Okay, yeah. Well, give me a number. Any number.
3.
3. Square 3. 9. Okay. Okay. So 9 is the square root of 3, right? No, 3 is the square root of 9. Okay, so if you do 9 divided by the square root of 9, which is 3, you get the square root of 9, which is 3. Right? Any number that will work. A square root times a square root gives you this thing under the square root, right? Square root of 2 times square root of 2 is 2. Square root of 17 times the square root of 17 is 17, right? Because the square root is a thing that when you square this number, you get what's inside, right? So when you square a number, you multiply it by itself. So if you multiply this by itself, you're going to get the thing that's inside, right? So that's where that comes from. So on your calculator, do the square root of 2/3 while I mark her up here. All right, double the class size, just like that. Okay. What is the square root of 2/3? Probably something around 0.8 or something like that.
Yeah, 0.81.
Okay. Now, that number there, 0.81, whatever you got on the screen, take the inverse cosine of it. Now, depending on what mode you're in, are you in radian mode or degree mode? Radian mode, okay. What do you get as?
Do I need to change it to degree mode?
Equal what?
Do I need to change it?
I can't hear you.
Do I need to change it?
I'm sorry, I still didn't knock it out.
Do I need to change it to the something else?
Yeah, you need to change it to radians.
Oh, wait, no. What do you have? Are you in degrees
I'm
or
in
radians?
radians. So I change
You're in radians, that's fine. What do you get as the answer in radians? Theta is approximately equal to 0. You just do the inverse cosine of whatever number you had on the screen. 0.81, whatever you said it was. Inverse cosine of that. 0.9 something?
Yeah, I have 0.9.
9999? Oh, so it's about 1 radian. Is that right? Is that what you're telling me?
Yes.
Okay, let's see.
2/3 is square root.
Oh, wait a minute. That's not what they give me. Did you see arc cosine or arc sine?
I did.
And by the way, they do it in degree mode. So let's go back and get in degree mode. Go back and do the square root of 2/3. That's about 0.8 something another, right?
I got 0.668.
0.6 something. That sounds better. Okay. So that in radians, let me erase this. Okay, 0.6 something another. Okay, 6 blah 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 radians. Okay, change that to degree. I didn't know they did it in degrees here, but what's that in degrees? Wait.
I think he was a degree. That's why he got the 0.99. I got
Okay.
Now I got 0.99.
Okay, right, okay. If this theta was 0.6 in radians, that's not 0.9 in degrees. Okay? It's not. Okay. Because 1 radian is around 57 or 58 degrees, and 0.6 of that is definitely not 0.9999. Okay. So go back to, okay, get in degree mode to begin with. Get in degree mode. Okay. Then do the square root of 2/3. And that we said was 0.8 something another, 0.81 something another, right? Then do an inverse cosine of that. In degree mode. Calculators versus what? what you get.
Got the same answer. I have the same answer. I have 0.99. I have the same answer.
All right. Are you in?
I'm in degree right now.
You sure you're in degree mode?
Yes.
Okay. How do I tell?
I see when it says D, and it says degree.
Oh, okay. Three. Yeah, I see. No. You did cosine. I said inverse cosine.
Oh,
Okay. Not cosine. Inverse cosine. Because this says cosine of this is this, so to get theta, you do the inverse cosine. Oh, I said
I have
that.
1.
Huh?
1.
Okay. Inverse cosine of 0.9999? That's not what you want. Okay. Go back. Okay. Be in degree mode. Okay. Now, take the square root of 2/3. That's 0.81, blah, 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 blah. Right? Square root of 2/3. In degree mode, okay? Square root 2/3, right?
Yes.
Okay. Now do the inverse cosine of that number that's on the screen. 0.8, blah, 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 blah. While you're in degree mode. Not the cosine of it, the inverse cosine. What do you get?
I have a bigger number now.
You got what?
I have a big number. I got 34.9.
Second?
34.9.
35.3 is what they have.
Okay, I got 34.9.
Okay. Well, they got 35.3. I don't know how they did it, but let me see how you did it. Let's see if there's a big difference. Okay. Okay, you rounded to 0.82, right?
Yes.
Okay, let's go back and do okay. 2 divided by 3 equal. Okay. And let's do a square root of that.
I'm saying you got it for 3.
Okay. 2 divided by 3. Okay. Square root of that. Okay. No.
You want this one?
Yeah. Okay.
Should be like
Okay, there it is. Okay. Now let's do the inverse cosine of that.
Yeah. You can't just put it.
Inverse cosine of answer equal. No, there's supposed to be inverse cosine. Oh, okay. Oh, I should have done that. Sorry. Let's clear that again. Okay. I'm going to try it this way this time. 2 divided by 3 equal. Okay? And then we're going to do the square root of answer equal. There it is. And now let's do the inverse cosine. That makes me shift. Shift cosine. That's what I did wrong. Of answer equal. 35.26 is what they got. 35. What did I say it was?
34.3.
No, they got 35.3. 35.3. So you see, you rounded earlier. They didn't. Well, they rounded later. So 35.3 degrees. That's it exactly. Okay. Okay. Finally. Okay. Did you get it now too?
Yeah.
Okay. Right. Good. They rounded 35.3. Okay. Let's clear my stuff off. Let's see how they do it. First, they rewrote that as a function equal to 0. So they subtracted 1, which doesn't matter at all if it's a 1, because when you do the gradients, the partials, the 1 isn't going to contribute a thing. -1, whatever. Okay. So you take the gradient of that and then substitute in the 221. They did it all in one step.
The gradient is the partial, right?
The gradient is the partial. Okay, the gradient is a vector quantity, and it's going to be the partial of this thing with respect to x. Well, this is going on with x in it. So it's going to be x over 6 in the I direction. Oh, there it is. They've written it here. Okay, yeah. And y over 6 in the j direction, and 2/3 z in the k direction. Right? That is the partial at any point x, y, and z. And then when they plug in the point 221, that becomes 1/3 I, 1/3 j, plus 2/3 k. That is the gradient at that point. That's in the maximum, the direction of maximum increase, which is by definition normal to the surface, which would be by definition normal to the tangent plane at the surface. Okay? Guaranteed. Okay? Now, what you do now, because that is normal to the tangent plane, k is normal to the xy plane, it follows that the angle of inclination, this is the formula they gave us there, is the absolute value of the dot product of this vector here and the k vector. And the k, of course, is 0, 0, 1, right? In components. Divided by the magnitude of that vector right there, okay? So what we're going to do, that dotted with the k is just going to be 2/3, okay? Because 0 dotted with 1/3 is 0, 0 dotted with 1/3 is 0, and 1 dotted with 2/3 is 2/3. Then you divide that by the magnitude of that thing, which is the square root of 1/3 squared plus 1/3 squared plus 2/3 squared. And that's what we did before, right? Is there a question? Okay. Okay. So that would be 2/3 divided by, and what we did before, this would be 1/9 plus 1/9 is 2/9 plus 4/9 is 6/9. 6/9 is 2/3. The square root of 2/3 into 2/3 is the square root of 2/3. We did that, remember? Okay. So that is going to be the cosine of the angle theta. So then what you do is take the inverse cosine of that thing to get the angle theta. The arc cosine or inverse cosine of square root of 2/3, and that's the 35.3. 35.3. Okay. Now, they show the figure here, and if you can tell anything about the figure, I can't. This is, remember I said this is sort of like a flying saucer, squatty on the z-axis and circular on the xy plane, okay? And you got the surface point up here, 2 out on x, 2 down here on y. This doesn't look like it's making any sense at all. 2 on x, 2 on y, and then up 1 on z. Yeah, so that's about right. It's hard to see where it is three-dimensionally when it's a two-dimensional board. It looks like it's sitting right over 0, 1, 0. No, it's not. It's up above that, you know. Come out 2 here, down 2 there. So that would be right here, then go up 1. That looks like it's a lot more than 1, but you know, that's what it's supposed to be. Okay, now, the normal is the gradient. It's one of the normal vectors, okay? It's normal to that surface there, so it's normal to that plane there, and the k vector is normal to the xy plane, so all you do is dot this normal with that normal, and you get this angle here, which is the same as the angle between the x-axis and this plane. Okay? And then divide by the magnitude of that, okay, of that vector there. Remember to do that, because otherwise it's not going to work well, okay? All right. Now, finally, a comparison of the gradients of f of xy and capital F of xy. Remember, this is when you have z is equal to f of xy. And this is when you have f, capital F, is equal to little f minus whatever your z was, whatever is on the other side. So here's going to be a comparison of that. This section concludes with a comparison of those two gradients. We know that the gradient of a function f of two variables is normal to the level curves of f, okay? Specifically, theorem 1312, which if you go back several pages. In fact, it's in the last section. There it is on page 926. Gradient is normal to the level curves. Okay? Well, that's saying the same thing we just said. So that's nothing new. Okay? Specifically, theorem 1312 states that if f is differentiable at x0, y0, and del f is at x0, y0 is not the zero vector, okay, then the del of f of x0 is normal to the level curve through that point. Okay? Oh, there it is. They repeated it here. You didn't have to turn back. Gradient is normal to level curve. So f is differentiable there. Del f is not the zero vector. That is normal to the level curve. Why did they repeat it twice? I don't know. Okay? Having developed the normal lines to surfaces, we can now extend this result to a function of three variables. The gradient is normal to level surfaces. If f is differentiable at x0, y0, and z0, then del f, okay, and del f is not the zero vector. Then del f, or the gradient of f at x, y, 0, is normal to the level surface through x0, y0, z0. Now, remember what a normal surface is. This f is a function of three variables. Okay? Now, so in other words, you can't picture f because that's in the fourth dimension. I can't picture that. I have no way of picturing that. Okay, but we just know that f is differentiable at that point. Well, there is a level surface there where all those f's are the same values. Okay? And this is a three-dimensional thing. So let's say that level surface is this kind of shape here. Okay? And if f is differentiable at this point here on that shape, then del f isn't the zero vector, which you never want that to be the case, then it's normal to that level surface. So if this surface is like this, your delta, your gradient is in the direction of maximum increase of that surface. Okay? Which is going to be perpendicular to it, normal to it. Okay? Blah. That's all they do. I thought they were going to do something else, but it's perfectly fine that they stop it right there. All right, that finishes 13.7. No. Okay. Homework exercises here include 3 and 5. They're both at Calc Chat. 5's at Calc View. Number 7 is at Calc Chat and Calc View. Any of the odds 9 through 15, they're all at Calc Chat. Any of the odds 17 to 25, they're all at Calc Chat. 19's at Calc View. Any of the odds 27 to 31, they're all at Calc Chat. 27's at Calc View. Either 33 or 35, they're both at Calc Chat. 33's at Calc View. Any of the odds 37 to 41, they're all at Calc Chat. Do 43, it's at Calc Chat. Do 45, it's at Calc Chat. You can explore doing 47, it's at Calc Chat. And then any of the odds 49 through, let's say 49 to 55, they're all at Calc Chat, or they should be. Now, some of those you'll need a computer algebra system or something like that to do an analysis. If you've got access to it, use it. I don't, so you don't have to if you don't want to. Now, writing a tangent plane, we did some of those. Do any of the odds 57 through 59, 57 or 59 for sure. You can try doing 61. That's a little more involved problem. 63 is a proof if you're interested in that. And then there's a section project. If you want to look at that, you certainly can. I doubt if that's going to be at Calc Chat. Okay? We're through with 13.7. Yay. Okay. Let's move on to 13.8. Now, let me see what the time is. Yeah, we got plenty of time. Okay. Yeah. Okay. So let's end this and go to that. All right. Okay, we're continuing chapter 13, which is functions of several variables. 13.8 is extrema of functions of two variables. Okay, now we did this back in Cal 1 when we did max and min with f is y is a function of x, y is a function of x, right? Okay, f of x. Okay, we did that. Take a derivative. Set it equal to 0. Blah blah blah. Okay. Now we're going to do this for two variables. Okay, so what we're going to do is find the absolute and relative extrema of a function in two variables. We're going to use second partials to test the relative extrema of a function with two variables. Just like we did second derivatives to see whether it was concave up, concave down, increasing, decreasing, those kind of things. Okay? So we're going to do something parallel to that in two variables, x and y. So let's look at absolute extrema and relative extrema. Extrema, you realize, is the plural for extreme, right? Rather than saying extremes, you say extrema. Okay. Now, consider the continuous function f of two variables defined on a closed bounded region R in the xy plane, and the values alpha AB and alpha CD. Okay, A being the x coordinate, B the y, C being the x coordinate, D being the y. Okay, such that alpha of AB is always less than or equal to the rest of the alpha of xy's, and that's less than or equal to alpha of CD. So this is going to be on that little region you're dealing with, however it's defined. This is going to be the absolute minimum, and that's going to be the absolute maximum. All the others are in between those values. Okay? And A, B, and C, D are in that region R. Now they've drawn it as a rectangular region R, which is fine. It's really easy to work with. Okay? Now, according to this graph here, your maximum is going to be up there, so that's going to be your CD right there. This is C on X, D on Y. Okay? Your F value is at a max. The F of AB, just looking at this, could be any one of these 4 points, because they look like they're all the same distance. I don't know if they are, but they look like they are. Okay? So it could be any one of those. All your rest of your f of xy are going to be the rest of the points here, not that one and not those minimum. Okay? Now, for all of xy, R are called this is the minimum, that's the maximum of f in that region. Okay? On that region R. Make sense? Okay. Now,
You said the minimum was.
I can't tell looking at this. There's a part of me that wants to say these two look a little shorter than these two, but I don't know that for sure. It could be these are closer to me, so they look longer. But one of those, or all 4 of those, one or more of those 4 points look like the absolute minimum. That's the absolute max. They say this is the minimum, fine. I don't know, maybe.
I was thinking they point at all 4.
What's that?
That was all 4 of them.
It could be. I don't know. It looks like it could be. Or it could be that is indeed less than any of the others. I don't know. But that's one of the minimum anyway. So this is the minimum. That's the maximum. For sure, that's the only maximum. Maybe more than one minimum, but on this case. Okay? Now, if this it looks like to me a tent covering, right? Well, if this tent covering did this and this, then there could be more than one maximum too. Okay? But it doesn't. On a rainy day, you don't want it to be. Anyway, okay, never mind. All right. So, I'm trying to... here we go. A region in the plane is closed when it contains all of its boundary points. So let's go back to this region here. If all these boundary points here were included in that region, that's called a closed region. And they said a closed bounded region R, meaning all these points here are on it. If they weren't, this would be a dotted line here, a dotted line there, a dotted line there, a dotted line there, meaning the boundary points are not part of the region, okay? But this one is a closed region. Why they brought that up, I'm not sure right now, but it's probably going to be important later, okay? A region is closed when it contains all of its boundary points. The extreme value theorem deals with a region in the plane that is both closed and bounded, okay? Now, what does the bounded mean? That means it doesn't head up to infinity and never come down again, okay? So if you had something, let's go back here again. If this thing just suddenly took off up here and then came from down here or went up here too, but they never meet, that would not be closed or bounded, by the way. Okay, it would be closed if all these boundary points were included, but you see the in-between point would be. So it can't go to infinity, okay? That's what it means by bounded, either positive or negative infinity. A region in the plane is called bounded when it is a subregion of a closed disk in the plane. Region in the plane is called bounded. Okay, that may not be what I was talking about then. When it's a subregion of a closed disk in the plane. Okay. Means it's bounded everywhere. Okay. So here's the theorem, 1315. Took a little trip. The extreme value theorem, let f be a continuous function of two variables, x and y, defined, and I don't know, every now and then they just have these vertical lines in there. I have no idea why it's there. It has nothing to do with my cursor or anything else. It's just a vertical line. It has to be, but I don't know why it's there. It has no meaning. Okay, on a closed bounded region R in the xy plane. F is a continuous function, two variables x and y, defined on a closed bounded region R of the xy plane. Now, the saying that it's continuous prohibits from having a vertical asymptote-like thing somewhere. You can't have that. That wouldn't be continuous. So it's a continuous function on a closed bounded region R in the xy plane. There's at least one point in R at which f takes on the minimum value. Maybe more than one, like all four of those corners could have been minimum values. There's at least one point in R in which f takes on a maximum value. Okay? There could be more. Okay? Like if it was hanging down from the four corners of a sheet hanging down. Okay? That would have four, or two, or one, or three maximum points. Okay? And one minimum, perhaps, or more. Okay? Because if you were over here and someone who weighs the same amount over here, you both have minimums there where you suck down in the middle. Okay? So, anyway, there may be more than one. Now remember, it's a closed bounded region R, meaning the boundaries are included. The minimum is also an absolute minimum, and a maximum also an absolute maximum. A minimum is also called an absolute minimum, and a maximum is also called an absolute maximum. As in single variable calculus, there is a distinction made between absolute extrema and relative extrema. Okay, here's the definition of relative extrema. Let f be a function defined on a region R containing x0, y0. Okay? The function f has a relative minimum at x0, y0 if for values of x and y around that f of xy is always greater than or equal to f of x0, y0 for all x's on an open disk containing that point. So let's say here is our bounded region R, okay, covering a big thing here, and the function is a relative minimum of x0, y0, meaning right here, x0, y0, right there. The function hangs down there, okay? And all the f of xy's around that are greater than f of xy at that point, okay? In other words, it's less than all of it. Out here, it could be lower somewhere else. But right around that point, on some open disk containing x, y, 0, 0. Not the whole place, some open disk there, around there, every other f of x, y is greater than that bottom point. Okay? Picture the sheet hanging down from the four corners. You're in the middle of the hammock. Okay, and where you are in the hammock, your big butt down there, that's the minimum. Everything else is above that. Okay? All right. Now, the function f has a relative maximum at x0, y0 if the f of x, y's, all the other f of x, y's around that f of x0, y0 are less than that. Okay? You're holding it up with something here, okay? And everything else around there. Maybe a more maximum here or over here or somewhere else. But right here, that little closed disk around, or open disk around there, it's the highest point. Okay? That makes it a relative maximum. For all the x, y's in some open disk containing x0, y0. Okay. To say that f has a relative maximum at x0, y0 means that the point x0, y0, z0 is at least as high as all the nearby points on the graph of z is equal f of xy. That means z0 is at least as high as all the others close by, nearby points. That's pretty nebulous, but nearby points. There is no z greater than z0, okay, for all nearby points. Similarly, f has a relative minimum at x0, y0 when x0, y0, z0 is at least as low as all the nearby points on the graph. That means all the other z's close by to x0, y0, all those other x, y's close, this z0 is less than all the other z's. Okay? So here is, this looks like, almost like an egg carton, right? Okay, or something like that. There looks like the absolute maximum. But here's a relative maximum, there's a relative maximum, there's a relative maximum, there's a relative maximum, there's a relative maximum. I can't tell the minimums, but somewhere down there is a relative minimum. Somewhere right in here is a relative minimum. Somewhere down there is one, and there's one. Does that make sense? Oh, wait, he's still my heart. Okay. Who is this guy? I've seen him somewhere before. Okay? Okay. All right. Yes, and we've got at least 10 minutes for class left. Okay. Okay, so that's what we mean by a relative extreme. Every one of those, max or min, goodness gracious, keep coming. It must be early. Okay, all right. All right. Every one of these is relative extreme. These are the maximum, these are the minimum. So you understand what it means? All right. Easier to see on a graph, okay, than me waving my arms. Okay. To locate the relative extrema of f, as max or min, you can investigate the points at which the gradient of f is 0. That's just like derivatives, right? Okay? Or the points at which one of the partial derivatives does not exist. Okay? Doesn't that sound like the relative maximum or minimum? They were where the first derivative is 0 or did not exist. Remember? Those are called the critical values, critical points. Okay? Such points are called critical points of f, the two-dimensional value. So the definition of a critical point, let f be defined on an open region R containing some point x0, y0. The point x0, y0 is a critical point of f if one of the following are true. If the first partial of f with respect to x at that point is 0, and the partial of f with respect to y at that point are 0, they both have to be, that's the critical point. Okay? Or f of xy, f of x at x0, y0, or either one, f of y at x0, y0 does not exist. So either both have to be 0 or either doesn't exist. Okay? Those are the two conditions, I might say 3 conditions, under which that could be a critical point. So, if f is differentiable, you can take the partial derivatives of it, and del f, which is your gradient of f, x0, y0. Remember, f is a scalar function. Del f is, the gradient of f is a vector function, and this f of first partial of f with respect to x, and x0, y0 I, plus first partial of f with respect to y, and x0, y0 j. If those are 0, 0, in other words, that is a zero vector, okay, then critical point. Then every directional derivative at x0, y0 must be 0, okay, because it doesn't matter what the others are, okay. That implies that the function has a horizontal tangent plane at that point. In other words, right there it is, okay. Relative, your partials in both x and y direction are 0 there, horizontal tangent plane, or 0 here, horizontal tangent plane, okay. That would be where you're, okay, now what is this telling you? That the maximum rate of change is 0. In other words, at that point, there is no direction that gives you a maximum rate of change. It's 0, okay, meaning horizontal tangent plane. So that's what the gradient tells you, the direction of maximum increase. And if that's 0, 0, then means no maximum increase. It's not increasing in any direction. Okay. It appears that such a point is likely a location of relative extrema. Okay? This is confirmed by theorem 1316, which is the relative extrema occur only at critical points. If f has a relative extrema at x0, y0 on an open interval, open region R, then x0, y0 is a critical point of f. Okay? Now, if it's a critical point of f, that doesn't guarantee it's going to be a relative extremum. But if it is a relative extremum, it does guarantee it's a critical point. Okay? So here's example 1. All right. I think we have time for it. What you reckon? Determine the relative extrema of this function. F of xy is equal to 2x squared plus y squared plus 8x minus 6 plus 20. 6y minus 20. Plus 20. Whatever. Okay. What's the first thing you're going to do? Say again? Zeros of that? Okay, find the gradient of it. Just like before we did derivatives, now we do a gradient. So what is... Okay, the gradient is taking partials. Right, okay. So let's do the gradient of f of xy. Okay? And that's equal to what?
So it's going to be 4x.
4x plus 8. That's in the I direction. Plus 2y minus 6 in the j direction. Okay? The 20 doesn't enter in the picture. What's that? There is no k. There is no z. We're only dealing right now with two-dimensional things. Yeah. Your k is the direction of f. F is your z value. So we're only looking at the derivative of z with respect to f and y, basically. Okay? Just like f of x, y is equal to f of x. You weren't changing y, you were changing x and get maximum min of y. Now we're changing x and y and get maximum min of z. So you only have two independent variables. Okay? Now, for this to be a relative extrema, both this has to be 0 and this has to be 0. So solve both of them. 4x plus 8 equals 0. What would that yield?
It's going to be negative 8 divided by 4.
Okay, yeah. 4x is equal to negative 8. Is that what you said?
Yes.
Okay, divided by 4. And that gives you x equal negative 2 and y, say again, 2y minus 6 equals 0. Okay, y is equal to 6 divided by 2, which is 3. So at the point x0 is equal to 2, negative 2, y0 is equal to 3, there you have a critical point. Okay? We think that's also a relative extrema. Okay? Now, do we have a clue of whether it's a minimum or a maximum? Not without further work. Okay? So x equal minus 2, y is equal to 3.
Is this where we have to choose a point above it and point below it to see which one?
Okay. That's one way to test. Let's first figure out what z or f of xy is at that point. So what is f of xy? We don't have to do this, but since you brought it up, what is f at negative 2, 3? What would that be?
It's going to be
8 plus 9 minus 16 minus 18 plus 20. Okay, running out of room there. Okay, so minus 16 minus 18 would be minus 34, and 20 plus 17 would be plus 37, so that would be plus 3. Is that right? I'm doing it in my head, so I'm not real fast at it. Okay, now you could test some other points close by and see if they're more or less than that, like at minus 1, 2, or something like that. I don't know if that's close enough. I think it would be. So you could test that one and then have a clue, but then you would have to test some others nearby and make sure it doesn't go like this here, but then go back up here. You know, it could be doing lots of weird things. So it's not real clear, and it's not real easy to tell by just testing other points. But we do know at that point is 3.
So what's the probably way to get track?
A really easy thing, just plug in zeros there. At the origin, it's plus 20. So I have a feeling that's a minimum. I may be wrong, but I think it's a minimum. Okay? Because at 0, that thing is 20. So that's sure less than 20. So I'm going to guess it's a minimum. But they didn't ask us that. They just said, determine the relative extrema. Okay? So let me clear this out of the way and see if we did it right. Okay? Okay? Begin by finding the critical points of f. Okay? So we found f of x, blah, blah, blah. And we found that the critical point is negative 2, 3. By completing the square for f, you can see that for all xy not equal to negative 2, 3, everything else is greater than 3. Now, they didn't say anything about that. Let's go back and see if we can figure out what they're talking about. Okay? By completing the square in x and y. Okay? Yuck. I'm going to call this 2 times x squared plus 4x. You see what I'm doing here? Factoring out the 2 from these two x terms. And I'm going to put a plus blank. Okay? Plus y squared minus 6y plus blank plus 20. Now that's the same thing I had to begin with, right? 2x squared plus 8x plus y squared minus 6y plus 20. That's the same function, right? That's f of xy. Right? Okay, let's complete the square here. Remember how to complete the square? You take half of the linear term, the coefficient, that's 2, and square it, that would be 4. Okay, I just added 4 here, but that's actually adding 8 because it's 2 times 4. So if I add 8 here, I better subtract 8 here, right? Now I've still got the same thing, right? I added 8, but I subtracted 8. So it's still the same function. Buy that? Okay. Let's do the same thing here. Take half of this term here. -3, square that, plus 9. So I just added 9, so let's subtract 9. Okay, what do we have here? 2 times x plus 2 squared plus y minus 3 squared plus 3. There's that shows up again. Okay, that's my f of xy. All right. Now, and sure enough, when x is equal to -2 and y is equal to 3, that's equal to 3. We determined that before. Okay. Now, what else does this tell me? Let's let the x go one more to the right. This is going to be something greater than, see, when x is equal to -2, that's a 0. And y is equal to 3, that's a 0. You do any x other than -2, and this is going to be a number not 0. That you square it, it's going to be positive. Anything other than that positive 3, anything other than positive 3, a little bit more or less, doesn't matter, that's going to get bigger. Okay, so any point on either side of -2 and positive 3 is going to make this a bigger number. So therefore that has to be a relative minimum. You see that?
I'm trying to.
Second?
I'm trying to.
You're trying to? Okay.
Yeah, I'm trying to.
Okay. Okay. Do you see that at the point we found out, okay, -2, positive 3, that was our critical point, right? Okay. At that point, this is going to be 3. Because that'll be 0, and that'll be 0, right? Okay. So this will be 0 plus 0 plus 3. So this function is going to be 3, right? 3. Okay. Now, any point plus or minus of x, just a little bit plus or minus of x, and of -2, and this is going to be, when you square it, that's going to be positive. Multiply 2 by it's going to be positive. And any point plus or minus of 3, even just a little bit plus or minus of 3. Okay, this will be positive. And squaring it will be positive. So this thing will be some positive number plus some positive number plus 3, that's going to be greater than 3. Right? Every one of them. Okay? So therefore this has to be a relative minimum. Because at -2, 3 is the lowest point it'll go. Make sense? Yeah. Okay. Yeah. All right. Okay. Okay, we did that. We did that. By completing the square, we did that. Okay? Any point other than -2, 3 is going to be something greater than 3.
So
Okay.
will it always be one of those numbers, the x or the y?
Okay. The critical points are when those partial derivatives are equal to 0. Okay? Now, and what is your question relative to that?
I would say like the relative minimum was 3. So will it always be a number in the x or y? Will it always be the x or y number?
Okay. Are you talking about this 3 here?
Yeah. Yeah.
Okay. Okay, where that 3 came from was from here. Let's see. Well, maybe they didn't do it. We did it. Okay. Okay. When you completed the square and got this, okay? Remember, it started off being a 20, then we subtracted 8 from it and subtracted 9 from it. That's where the 3 came from. Remember? Okay. That was part of the problem. That came from the very first equation. It started with being a 20, but then we had to subtract, and it got down to 3. Okay. Now, when you plug this value in here from completing the square, it just happens to be that this right here makes that a 0, and this makes that a 0. Okay? So that's as low as this will ever go. It'll be 3. Anything on either side of any one of those points, just anywhere there, and these things don't get greater than 0. And that will be greater than 0. And adding it to 3 will be something greater than 3.
All right. So yeah. It could have been this.
I hate to say that, but yeah, I think it would be. Yeah. Okay. Depending on your problem. Okay. So a relative minimum occurs at -2, 3. Okay. Now, all of them may not work out that easily. Okay. Can't say that they will. I would suspect they don't. Okay. So the value for the relative minimum there is 3, as shown in this figure. Yeah, I was getting ready to graph that, and they did it for me. Shucks. Okay. Now, actually, that completing the square was how we found out what the xy plate was. That's where x equaled -2 and y is equal +3. That is your minimum. That's the critical value would be here. Go up and find it here. That would be 3 on the z-axis. So there's that. And from there on, you have a paraboloid. Okay? This is a definition of a paraboloid. Z is equal to something in x squared, something in y squared, plus or minus something. That just elevates it up or down. That's a paraboloid centered at -2, 3, and the z component would be at 3. The lowest value would be at 3. So that, sure enough, does describe that figure. Okay? That's a translation in x, a translation in y, and a translation in z. Okay. And everything else is greater than that. All right. How are we doing? Past time, right? Sorry about that, folks. By the way, there's a guy mentioned here, Carl Weierstrass. Although the extreme value theorem had been used by earlier mathematicians, the rigorous proof was made, the first rigorous proof was made by Carl Weierstrass. He also provided rigorous justification of many other mathematical results. Say again? Let me spell it for you, the last name. Weierstrass.
That's his last name?
That's his last name. His first name was Carl with a K. Good German name. Okay?
S-T-E-R?
Say again?
It's a W-E-I-E-R-S-T.
Okay. Weierstrass. If you're at all familiar with German, Strasse is usually street. That, like it was Karl Weyer Street. I don't know what that would mean, but that would be what it would be. We did example 1, and by the way, you can go to larsoncalculus.com and see an interactive example of something like example 1. Next we'll do is example 2 on page 942. That's where we'll begin next time. Well, yeah. So before we get to second partials test, we'll need to do example 2. Okay? Good deal. One other major, wait, yeah. There may be some homework exercises we can do here. Let's see if there, oh, yes, look at this. I think you can do any of the odds 3 through 7. They're all at Calc Chat, 7's at Calc View. And stop there, we'll do the rest of them later. But there's one other assignment. Have a great Thanksgiving. Okay? You all know, I'm sorry to break this news to you, there's no classes next week. We just got you back. Okay. So, all right. Good deal.
Too bad, man.
Huh?
Too bad.
I know. It breaks my heart. Okay. Have a great Thanksgiving. I would say don't eat too much turkey, but I'm not going to put that on you. Eat as much as you want. But be awake when you come back Monday. Okay. Sleep it all off before Monday. Okay. I'm talking about the turkey. Okay. Hey. You mean the dressing and stuff? Oh, I see. Okay, got it. All right. I recorded all that, by the way. Okay.